Alright, so good morning everybody and welcome back. Now your class notes will be almost the same as the ones that I have up on the screen. The only thing that changed is there's actually kind of a title slide on some of these. And that's so that anybody who looks it up online can actually figure out what we are talking about. Right? You have the advantage you saw the name of the file. So we are going to talk today about handout 2, crystals. And the first thing we need to ask ourselves is, what is a crystal? Any ideas? It has a certain arrangement of atoms, yes.
It's in a solid state.
It's usually in the solid state. That's certainly a good thing. I haven't seen many gaseous crystals, I agree. It has some kind of repeat structure.
Usually has a defined geometry.
Usually has a defined geometry. Very good. You guys are up to this. As a matter of fact, the oldest definition of a crystal was way before what we call crystallography nowadays. And that was simply a solid with well-defined faces. And I brought some examples of those. Okay. These would have been considered solids with well-defined faces. I assume we all agree, right? It would be pretty easy to describe the shape of most of these pieces. And we'll pass them around a little bit later, once we've introduced a few more things. So, that's the old definition. In crystallography, as some of you already kind of pointed out, we usually talk about a crystal when we have a material with a regular repeating structural motif. So that is what several of you were hinting at when you said it repeats. It has a regular arrangement. If you take a really strict definition, it's a bit more vague, okay? It would be any material that gives a sharp diffraction pattern with peaks, a diffraction pattern with sharp peaks. Now, as we will see, things that fulfill this will also fulfill this, okay? And that's what we are here to learn about. So what is that repeating motif that we were talking about? In crystallography, we call it a unit cell. What a unit cell is the smallest entity of the crystal that you need to describe. And when you
product properties of the crystal.
It has an influence on the properties, but there are more things than that. It's also what is within the unit cell. Okay, it's not just the size and shape of that unit cell that determines what the properties of a material are. But that is the smallest repeat unit, so if we can describe the size and the shape of this repeat motif, we can really describe the whole crystal. It's kind of like playing with Legos, right? Once you have one piece, you can start repeating it. You can build whole big structures out of it. So you can build whole big crystals out of your little repeating motif called unit cell. One thing to keep in mind, when you deal with unit cells, by definition you always use a right-handed axis system. So we call the three axes A, B, and C in crystallography, and it always has to follow a right-hand rule. So if you've decided which direction A and B point, you don't have a choice which direction C has to point. Okay? So in this example, A and B are here and here. So this is the direction of the rotation. You point your fingers of your right hand along that direction. The C-axis has to point up in this case. You cannot draw the C-axis as pointing down. That would be a left-handed axis system. And that's kind of the convention that most mathematicians use too, right? So we've encountered that at some point in time in our life. Always use a right-handed axis system. Now this drawing actually shows you that we have more than 3 variables to describe our unit cell. We have A, B, and C. We also have 3 angles, alpha, beta, and gamma. Alpha being the angle between B and C, beta between A and C, and gamma between A and B. Now, what kind of shapes do you think we can actually create out of that? How many different shapes can we create if we use A, B, and C and alpha, beta, gamma? Any idea?
Seven types.
You say 7 types. Any other opinions? I put one of you up to just decide 6 random values of A, B, C, alpha, beta, and gamma. Put a second person up to do the same. How likely that the two pick the same? Not very likely. Now we have what? About 10 people in this room? If I gave you that assignment, what do you think? How many different combinations would we come up with? Probably 10, right? So in that case, we already would have 10 different unit cells. But, as Anil correctly pointed out, there's a 7 somewhere in there. Now, what's that 7 refer to? Well, we can group these different unit cells according to the relations between these A, B, C, alpha, beta, gamma values. And that is what leads us, correctly, to the 7 crystal systems. Okay? Now, last lecture we had a slide up with a list of Nobel Prizes. Don't worry about ever memorizing them, okay? I'm not going to ask you about every single person who won a Nobel Prize. That's there for you to look at as an inspiration. This slide here with 7 crystal systems, you will need to memorize that one. I will expect you to know the 7 crystal systems. And these are ordered from highest to lowest symmetry. Now, what do we have? The highest symmetry repeating motif that we can come up with is a cube. And we call the system cubic. What does a cube look like? A, B, and C are all of equal length. Alpha, beta, and gamma are all 90 degree. And here's a little cube. Okay? What can we do with that cube? We can do a variety of distortions. And I'll actually first skip a couple here. Tetragonal and orthorhombic are very easy to derive from the cube. Tetragonal just means you change one of the lattice constants. 2 of them are still identical. You have a square footprint, but the third one is different. Could be longer, could be shorter. We still have all of our angles 90 degree. And this is the closest example I could find in my collection of a tetragonal crystal. Doesn't quite have sharp edges, okay? So if you looked at a unit cell, of course it wouldn't have these rounded off edges. They would actually be sharp edges. But that's a tetragonal crystal. Didn't bring an orthorhombic one with me, but the big difference there is all 3 lattice constants now are different. We don't have 2 identical lattice constants there, but all the angles are still 90 degree. Anybody know what kind of shape that is? It's actually something we meet a lot in everyday life. Brick, right? A, B, and C are all different, but all the angles are 90 degree. That's a brick. As a matter of fact, some people like remembering it as orthorhomb brick. Don't write that down as a crystal system on an exam though, okay? Leave the R out, leave the K in the end out. It's orthorhombic. But if that helps you remember it, hey, be my guest. So, those are the 3 systems that have all 90 degree angles. Then we have a couple up here in between. Hexagonal and rhombohedral. Hexagonal has 2 identical axes. By definition, we choose A and B as the identical axes, while C is different. In this case, only 2 of the angles are 90 degree, while the angle between the 2 identical axes is 120 degree. What that does overall is it creates some 6-fold symmetry, as we will learn later on. Now, this is not a unit cell, okay? I'm not going to lie to you. However, this might be a hexagonal crystal. And you could easily, quickly tell that it is hexagonal just by looking at it, couldn't you? It has the 6-fold symmetry. Somebody actually took a pencil and drew some lines on here. Okay? Either one of these could be a unit cell. The main reason being, the unit cell has to repeat in 3 directions. I cannot repeat this thing in 3 directions, because if I repeat in this direction, then I have tip to tip, and I have empty gaps in space. Okay, so we cannot do that. But if I take one of these smaller units and I just repeat it, I can fill all space. And this is just a crystal that happens to contain several unit cells. Okay? Now people would have called that one hexagonal way before they knew about crystallography. Okay? But if you look at the crystal, you know why they came up with that before they knew about diffraction and crystallography. Because that crystal has very beautiful six-fold symmetry. It's very easy to classify things according to that. So that's the hexagonal crystal. Rhombohedral is an interesting one. And that one is actually the most confusing one for a lot of people. Sometimes people call it rhombohedral, which is how it is usually listed as a crystal system. Sometimes you will find something that is called trigonal. It's actually the same as this rhombohedral one. It's a different setting of the unit cell constants. We will get into that as the classes proceed. For today, rhombohedral is simply a cube that you took and you either squished it or you kind of expanded it along a body diagonal. Okay? That's the easiest way to figure out what a rhombohedral crystal is. All axes are equal. All angles are equal. But they are not 90 or 120. Okay? So it's very similar to the cube in that respect. All axes equal, all angles equal. The difference being it's not 90 degrees. What does that look like? Well, it really doesn't always look like such high symmetry on first glance. I brought two rhombohedral crystals here. Okay? On first glance, at least this one looks a bit ugly. But if you look at this point, you will see that the three axes are identical, the three faces are identical, all the angles are identical. So one of them is squished, one of them is pulled along the body diagonal.
So they can't do 90 or 120?
If it was 90, it would no longer be rhombohedral, it would be cubic. If it was 120, you could actually also do certain transformations and get different crystal systems back. So that's why that comment is given here. It will not be 90 or 120 if it is a true rhombohedral crystal. So we are almost through the list of 7 crystal systems. 2 missing, and those are the ones that are certainly considered pretty low symmetry. Both of them have angles that are not 90 degrees. And for that matter, they don't have identical axes. A is not equal B is not equal C in both systems. The big difference is monoclinic still has 2 angles that are 90 degrees, while triclinic has no angles that are 90 degrees. Okay? Monoclinic, usually you choose beta to not be equal to 90 degrees. Okay, that's just convention. So if you read the crystallographic literature, you may actually find something that just tells you lattice constants A, B, and C, and beta is, for example, 95 degrees. They would expect you to recognize that that is a monoclinic crystal. They probably wouldn't even tell you that alpha and gamma are 90 degrees. So in crystallography, unless specified otherwise, the angles are either 90 degrees or in the hexagonal system, 120 degrees. Okay? The angles that are not 90 degrees are the angles that will be reported to you. So if somebody tells you this is a cubic system, they won't ever report angles to you usually. Because everybody knows that a cube has 90 degree angles. At least that's what they assume. And that's why we are here, so that we are part of that educated group of people who can actually figure it out. So, that's the crystal systems. How do you make crystals? Good question, right? Because if you want to do crystallography, at least single crystal crystallography, guess what? The first task you have is to make a crystal. Otherwise you really can't do any crystallography with it. What happens first when you make a crystal is an event that is called nucleation. A small nucleus forms. And usually this happens from solution when we talk about these things. Okay? And this event is actually the most difficult to control in many cases. Because pretty much everything else interferes with it. It's not just the compound that we have dissolved. It's not just the solvent. There are container surfaces. There could be a dust grain in our container. There could be a scratch in our glass. All of these things will influence the nucleation of materials. Okay? Now, how much control do you have over whether or not there's a dust grain somewhere? You have some, right, if you work very, very cleanly. But to some extent, that is outside your control. So sometimes the nucleation of a crystal is actually a serendipitous event. Okay? It may sometimes be difficult to reproduce what you did yourself. That's why you might have heard people sometimes kid around about catalytic amounts of dirt. Okay? They certainly can sometimes be your friend or your foe in crystal growth. What happens next is the growth of the nuclei. Alright? This could be isotropic, which means it grows equally in all directions, but in most cases it will not be isotropic. It will grow differently in different directions. What you will then see is a crystal that results. Now, one thing to keep in mind is the high energy phases will grow fastest, because high energy phases are not favorable in nature. Right? We all know that. So, whatever phase has the highest energy in a certain environment will grow fastest. That could be changed depending on what my environment is. Okay? Maybe in pure aqueous solution, one phase has the highest energy because the water molecules can't quite arrange there. Maybe if I switch to an alcohol, things change because the alcohol has a different structure, so it might be happier to coordinate on certain phases and reduce the energy of that phase. That also means that the shape of your crystal could depend on where it grows. Okay? That's a pretty interesting thing to keep in mind. And some of you may be getting into protein crystallography here, where you screen a lot of different growth conditions. And for the same compound, you can sometimes get very different crystal shapes. Okay? The reason for that is you have different solution additives. They change the relative stabilities of phases. Now, how can we figure out how big our crystal is? It really boils down to the relative nucleation and growth rates. What you want if you want to make big crystals is a low nucleation and a fast growth rate. Although you don't want a too low nucleation rate because you still want crystals to form, right? So you need to be above a certain threshold. But if you have a very fast nucleation rate, what you end up with is what people sometimes call a precipitate, which is a lot of very small crystallites. They aren't big enough to do single crystal studies with them. Okay? Are they crystalline? In most cases, yes. But you can't just stick them on a diffractometer as one single piece, because the nucleation was so fast that it consumed all the material in solution before the crystals could grow. So you need some kind of balance between these. Okay? Now, the part about the different type of shapes depending on growth environments is actually very nicely illustrated by these selenite crystals, which I borrowed from our friends on the third floor, the geologists. Both of these are selenite crystals. It's the same material. Okay? This one grew as needles. This one grew as what they call roses, but what it really is little plates. So what you can see is that there are two growth directions that are pretty similar, while one of them grows differently. Okay? If the one different direction is preferred, you get needles. If the different direction is disfavored in growth, you get flat sheets. So they can grow differently. But back to our original question, how would we go about growing them? Well, this is where those of you who want to go into crystallography have probably been looking forward to, oh yeah, we'll get the answer to how to solve our problems. Big disappointment, unfortunately. There is no one size fits all for crystal growth. It simply is not. Your choice of method will depend on your material, and pretty much, while there are certain guidelines, you will have to optimize the method for every single compound that you want to grow a crystal of. Okay? Now, there are of course certain common approaches, which is likely what you will try first. The most common way to do it is growth from solution. And I would assume that all of you have actually dealt with that, okay? Anybody ever done an organic chemistry lab where you were told to recrystallize something? Pretty much everybody in the room has, right? That is exactly what we are talking about. We heat something in a solvent, it dissolves, and this is usually some organic solvent or water, right? And then when we cool it, it starts to crystallize again. That's crystal growth from solution, right? Now, most people when they hear crystal growth from solution are thinking about exactly this: water, acid, base, organic solvents, mixtures of the above, something like that. But that's not all that there is to growth from solution. You could use a molten solid. Sodium chloride melts at about 600 centigrade, somewhere around there. Some metals melt very low temperature. For that matter, gallium is a liquid at room at just above room temperature, right? So you could grow crystals at 40 centigrade in molten gallium. If you're working with something like a protein or an organic molecules, chances are you're not going to try that, right? Because why would you assume that that material has better solubility in molten gallium than it does in an organic solvent? Well, probably not. But some of you may not be working with organic compounds. Some of you might be working with inorganic materials. They may not like to dissolve in normal solvents, as we call them. They may be quite happy to dissolve in some of these molten solids, okay? In that case, that might be a way of growing your crystals. The only requirement that you have for a solvent, whether it is what we traditionally consider a solvent or a molten solid, is it should dissolve the reactants, and in the best case scenario also the products to some extent. Because that way you can actually play with saturation of your solution and hopefully grow big crystals. Okay? So your choice of solvent depends on your material. As I said, you need to optimize it for every single problem. Another option is grow from the vapor phase. Okay? It's not very common, but it does exist. How does that one work? Well, this is one of the experiments that I actually did when I did an undergraduate organic lab. We grew menthol by sublimation, well, we purified it by sublimation. The material doesn't melt, it vaporizes from the solid state and it redeposits from the solid state. Well, in that case, obviously, I'm not going to grow from a liquid, right? I will grow from the vapor phase in this case. You can form very beautiful needles. It can also be used in a slightly different manner. So the menthol just vaporizes itself. For example, zinc sulfide reacts with iodine gas and it will form zinc iodide and sulfur. Now there's one solid here, everything else is a gas at certain temperatures, of course. Can you make zinc iodide a solid? Yeah, once you cool it. Right? Zinc iodide, most of you would probably have said that's a solid when I told you. For that matter, sulfur, when we cool it, what is sulfur at room temperature? Solid. So this is certainly an equation that is given at higher temperature, but it works. If you have zinc sulfide, it will not evaporate. Okay, it's a solid. It has a pretty high melting, or for that matter, vaporization point. These other materials can be easily vaporized. So if you heat your reaction container, you will actually be forming an equilibrium where you make zinc iodide. If you have another part of that container that is cold, you can deposit crystals over there. So it's all an issue of playing with your exact temperatures and temperature gradients. Now that seems to be something very abstract, not very common, not very useful. But this equilibrium is actually used in everyday life. Most of you are using it every day. Anybody any idea where? Have you ever heard about halogen light bulbs? It's one of those things we hear, right? We don't really think about it, we know they work, we put them in the fixture and we turn on the light switch. Why are they called halogen light bulbs? They do have some gas in there, and that gas is a halogen basically. Now, what glows? Is it the halogen? No. How does a light bulb work? What glows in a light bulb? The filament. What is the filament usually made of? Tungsten. So, tungsten, you pass a current through it, it glows. That means it gets pretty hot, otherwise it wouldn't be glowing. Tungsten has a very high melting point, okay? 3,400 centigrade, something like that. But, even while it has a very high melting point, there will slowly be some breakup of that filament. Some of it will actually evaporate over time. What does it do to our filament? It makes it thinner and thinner and thinner, and it will break. So in the old days, light bulbs didn't last that long, okay? Because the filament kept thinning and would break. So what people discovered is if you put some halogens inside that light bulb, you have a temperature-dependent equilibrium. You will actually make WX6, okay, where X is a halogen. Now that compound is interesting because it's only stable over a certain temperature range. When it gets hot enough, it will decompose into the elements. Now that's beautiful because basically you form this compound in the gaseous phase in the light bulb, but whenever one of these molecules touches the filament, it actually decomposes. Tungsten stays there as a solid, the halogen goes back into the gas phase. So this is kind of a catalytic reconstruction of your filament. And that is why light bulbs last a lot longer nowadays. So this whole vapor phase deposition process can actually be very useful. Now let's turn back to something more common. Okay? Probably if you're trying to grow a crystal, growth from the vapor phase will not be your first choice, because for many materials it doesn't work. What you may be trying is actually growth from a melt. And that is really a special case of growth from solution, because basically your solvent is the same as the material you're trying to crystallize. If you can melt a solid, should it be perfectly soluble in itself? Oh yeah, absolutely. So the only variable you have there is not really concentration but temperature. And so the idea is you have a melt, you slow cool it, you form very few nuclei who form coherent crystals. Once again, you control nucleation versus growth rates. However, it doesn't work for all materials. There are a couple of conditions. First of all, the material needs to be stable above its melting point. If you cannot melt a material without decomposition, you're not going to grow it from the melt. It's a no-brainer, right? The other part is you need to be able to directly crystallize it. And this is something where phase diagrams can be very handy. Now, how many people here have seen phase diagrams before? Wow, good. We actually have a lot of people who've seen them. For those who haven't, and as a quick reminder, let's look at some phase diagrams. So these are pretty simple ones of what we call binary compounds. They contain A and B. It could be two elements, could be two oxides, two halides, anything. What we have here is 100% A and 100% B. Each of them has a melting point. And then we have a phase diagram in between that tells us what kind of compounds we can form. In this case, the only compound we are interested in is AB with a 1-to-1 stoichiometry. If this is our phase diagram, we can attempt crystal growth from a melt, because this is what we call congruently melting. That means at composition AB we have a line that goes up all the way to this so-called liquidus curve. So if we have a melt with a 1-to-1 composition and we start cooling, we hit the curve here and we follow this line down. So life is good. Our material melts incongruently, as in this example, we cannot grow from the melt. Because if we had a liquid with a 1-to-1 composition, we cool down, so this y-axis is temperature in this case, we would hit the liquidus curve here. There is no line here. So we have to follow a line. Well, if we keep cooling, we follow this line. So what we'll do is we change the composition of the liquid and we deposit B. We will not be depositing AB directly. We can probably make some nice crystals of B that way, but that's no good if we want to grow AB. And of course, this one is very bad too, because this one has an upper limit of stability. Compound AB is not stable above this temperature, but A and B are both solids above that temperature. There's no way you're going to grow crystals from a melt for that compound. This one, if you play some tricks, maybe you run lucky and you can kind of go back from here and form some of this. That one, don't even try. So if you are working with inorganic solids, it's probably worth looking up these phase diagrams if they exist. So, if your material is not stable above the melting point, what can you do? Well, we can go back to this whole flux idea. As I said, that is usually a molten solid. Okay? The strict definition of a flux is that you have a liquid reaction medium. That doesn't mean liquid at room temperature, but at the temperature where you want to grow your crystals, that dissolves both the reactants and the products, but does not participate in the reaction. Now, with this method becoming more popular, the definition is often no longer used in the very strict sense. So you will hear people talk about a reactive flux. That means it participates in the reaction. Now, according to the original definition, it's not a flux, okay, because a flux shouldn't participate, but it has become fairly accepted that a lot of people will use that terminology. So if you hear somebody talk about a reactive flux, you know what it is. Okay? It's something that dissolves the reactants and the products, and that does get incorporated into the product. That is what people mean then. So it's once again something like a molten solvent, not a traditional solvent that is a liquid at room temperature, but something that is a liquid at the temperature where you form your crystals. What are the rules for picking your flux? Well, the number one rule is your reactants need to have some kind of solubility. Because if they don't, you're never going to grow anything. They'll sit there, stare at your flux and say, yeah, right. Why should we do anything? Why should we react? We are sitting at the bottom of the container. We are not going anywhere. You won't form crystals. Now, the good question is, how soluble do they have to be? Some people say, oh, you need high solubility or you'll never be able to make crystals. It's not true. If you have a few weight % solubility, you can often make crystals. The advantage is you have some of your reactant in the dissolved state. It can react, and of course, according to Le Chatelier, we will dissolve more of our reactant. So we will slowly dissolve it. It might actually help us control our reaction rate. Okay? If the product is slightly soluble, it improves your chance of making big crystals because the product can kind of redissolve and recrystallize. But it doesn't necessarily need to be soluble. You can grow crystals when only the reactants are soluble in the flux. So it can be very powerful. Why do we actually use a solvent at all? It's a good question, right? What it does is it improves the reaction kinetics. Things can interact with each other better. They are more mobile in the liquid phase, so if you have several reactants, if you actually can get them into any kind of liquid state, be that in a melt, be that in a solvent, they will have a better chance of reacting quickly. And most of us are not very patient, so we prefer the quick reactions, right? It also gives you the advantage that you can sometimes grow crystals at a lower temperature. Because we are in the liquid state at a temperature where things wouldn't melt. Okay? If you have a material, a target compound, like that AB in the upper stability limit phase diagram, that is not stable anywhere close to its melting point, then a solvent is really a good way to go. You can make materials that are not stable. Sometimes you can even crystallize materials that are not stable, even at their temperature range, but that are metastable. So kinetically, they happen to form. There might be another arrangement that is more stable, but this is the one that forms. Yes?
So would that react like catalysts
See, a catalyst usually forms a defined compound. This is not really forming a defined compound. They just put things in the liquid state. So, how far can you go by crystal growth from solution? Here's an example. This is certainly an optimized method, wouldn't you think? These crystals, I believe, were about 500 to 700 pounds. These are potassium hydrogen phosphate crystals. And they needed big crystals because they want to investigate the second harmonics generation of these materials. And they put some effort in there. Trust me, it took them a little bit longer than a week to figure out how to grow these crystals. It probably took them a little longer than a week to grow a crystal like that. But they sure make for pretty pictures, don't they? So, this is grown by what is the most commonly used method, at least in organic chemistry, from solution. What they did was they manipulated the saturation limit, because that is what determines your nucleation versus growth. What you really want is a saturated solution that you slowly cool. So you just hit that area where it is super saturated. So things want to crystallize out. But if you don't have a lot of nucleation sites, you form very few nuclei. And then you start depositing materials on these nuclei because they are kind of impurities, right? They are crystallization sites. They are a place where it is easier to deposit material. You can do that by slow cooling. It could be a temperature-dependent crystallization. You could slowly evaporate your solvent. You could slowly add something to your solvent that changes the solubility. Once again, that might be something that you encountered in organic chemistry, where you added a different solvent that had a different polarity, and your compound became less and less soluble. Okay? The slow evaporation can work very well, and sometimes when you forget about your reaction, it works the best. I once tried to grow some crystals when I was a grad student. Things just didn't work, and so I finally dissolved it. I think it was actually an alcohol in an evaporation dish, covered it with a watch glass, and I wanted to do a reaction that required open flames. Well, not a good idea, so I took it, I moved it somewhere else. I completely forgot about the fact that I had ever done this, right? So, about a month later, my lab book is full, and I decide to create a table of contents, so I go through it. And I find this comment that I dissolved this material, and I'm like, whatever happened to it? And it was like, oh, I moved that dish. So I went there, and about a month later, there was pretty much no liquid left, but they were beautiful big crystals. So sometimes not looking at them is actually the best way of getting them to grow. They were left in peace. They rewarded me with beautiful crystals. Sometimes you have to work on them though. What else can you do to make crystals? Well, there are certainly specialized methods. If a problem is important enough that people put the effort in, you can end up with something like those 700-pound crystals on the last slide, or with something like this. This is one silicon single crystal, believe it or not. This one weighs about 50 pounds. It's actually a small one. They can grow much bigger. Commonly grown with about 10-inch diameter and several feet in length. These crystals are usually grown by a method that is called Chochalski growth, according to the people who first started working on that. It works pretty well for semiconductors, so silicon, gallium arsenide, most of these are grown by these methods. It also works for certain oxides. You can do it with titanium sapphire, with neodymium yak. If you look at this, one thing that you will immediately notice is, are these materials that you've heard of in applications? Everybody knows Silicon Valley, right? So obviously semiconductors are important. Anybody any idea what these are? Laser materials, exactly. So these are materials where there is business. There's money in it. So people took the effort to optimize the crystal growth. Okay? Because otherwise you don't have good performance. How do you do it? What it really is a seeded growth. So what you have is a seed crystal that you attach to some kind of fiber or rod, and you will slowly pull it out. Of course, that means as you pull it out of the melt, it starts cooling, And so the crystal starts forming. And what they've done is optimize the temperatures and the pull rates to make the biggest and purest crystals that they can make. Is that going to work for all materials? Heck no. Your material better be very stable and not have too much vapor pressure to make that one feasible, right? But for certain materials it will make very nice big crystals. Now, truth be told, if you're a crystallographer who wants to determine structures, you don't want that one anyway, or the one on the previous page. How are you going to mount it? The crystallographer is going to say, are you nuts? You have to chip a piece off. So you may as well grow a more reasonable size to start with, right? There are some specialized methods that still refer to the growth from solution. Some of these are actually commonly used by people in organic or protein chemistry. What they make use of is vapor diffusion or solute diffusion. So what you have here is a very old traditional setup. You have a test tube and you have your compound in there, and it's dissolved in some kind of salt solution of a certain concentration. This example uses 0.5 molar ammonium sulfate. You use a beaker and you put a solution in there that is 1 molar ammonium sulfate. Sounds pretty trivial so far, right? You close that beaker off. Parafilm, watch glass, something like it. What happens? Well, this system isn't really at equilibrium if you think about it, right? We have a more and a less concentrated solution. So what will slowly happen is the two solutions will try to be at equal concentration. So some of this water in here, in the less concentrated solution, will evaporate and go into the rest of the solution. Well, that is just very slow, very controlled evaporation of your solvent. Okay? So if normal evaporation of the water is too fast, this may be a setup that helps. The same way you can do that with the so-called hanging drop method. You might actually have heard about that one. In that case, you have a drop of liquid with your solute in it up here. And once again, you have a more concentrated solution down here. What's the advantage of that one? Well, very easy to recover your crystals. Okay? Because it's up there on a slide. You flip it over, you have it right there on the microscope slide where you would like to have it. You could also work with layered solvents, where things can diffuse at the interface between the two solvents. Okay? This is especially useful if your reactants and your products have different solubility in the two solvents. So, now that we have some idea of how we make crystals, let's get back to the crystal habit. Crystal habit is what we call the external shape of a crystal. So that refers to those little things that we passed around, whether they are real-life crystals or little models. And this is what people classified crystals on before they knew about diffraction. The 7 crystal systems were established simply referring to the external shape of crystals. Later on it was found that there are good reasons why crystals form these shapes, and that will actually be what we are getting into in this class a lot. Now, what should you keep in mind? You will have visible faces and you will have corners. Now, the visible faces are actually not the fast-growing faces, which is something that is very easy to think if you don't really take enough attention to what you're talking about. A face that stays a face is not growing quickly. If it was growing quickly, you would have material depositing and you would form a corner. So the fastest growing faces will not be visible in your final product. As we already said, crystal habit can be affected by growth conditions. You saw those selenite crystals that we passed around. Now, that was just an example where the growth conditions seem to be the same throughout the whole process. However, what you also could have is very interesting crystal shapes depending on whether the growth conditions change. This is a calcite mineral, okay, what you will see is a bunch of crystals that all grow kind of like a hedgehog. But pretty much each of these is a fairly well-defined crystal growing out of the center. This one is actually the same material, okay, but if you look at these more closely, you will see that the big shape-defining things that you can probably see right now from where you're seated are similar to the ones over there, but then it looks like each of them is growing a little hedgehog on them. Okay? Very interesting crystal shape. How did that happen? Well, we started growing some crystals and then the conditions changed. So all of a sudden, nucleation became very fast. So you had a lot of new seeds depositing on the surfaces of these crystals, and each seed started growing. That is how you get this kind of hedgehog on the crystal shape. Now, one thing to keep in mind is the crystal habit can usually be related to the crystal symmetry. Why is that? Well, if you look at a cubic crystal, is there any reason why the 6 faces should be different on a cube? Not really, right? So, unless there is something that limits the growth, those 6 faces should grow at equal rates. Now, of course, if something is sitting on the ground of, a lake or some lava deposit, can't grow in that direction. But if there's nothing that inhibits the growth, it should grow equally in all directions. So it should preserve something that is related to a cubic symmetry. That could mean it preserves the faces. That could mean all these faces disappear at the same rate. How can that look? Well, here are some crystals of a compound called fluorite. Okay, some of them obviously have some other atoms in, so the color changes. But fluorite is a cubic material. Now, these aren't perfect cubes, so obviously there were things impeding the growth. But you can certainly see very well-defined faces. You can see 90-degree angles. And this one actually has a lot of little crystals that are a lot closer to the cubic shape. So, often looking at these crystals can give you some kind of idea of their symmetry. Now, cubes are pretty easy for most of us to recognize, right? You sometimes have to get a little more involved to actually figure something out. But people actually made this a science a long, long time ago. So what they found is that measuring interfacial angles on certain minerals could actually allow you to first of all figure out a crystal system, 90 degree, 120 degrees, something else, okay? Or in some cases it actually allows you to figure out whether something is or is not a certain mineral. How do you measure that? Well, they used a device that is called a goniometer. So here's a little crystal, this shaded thing, and you put it against the flat side of the goniometer. And then you line up the second face with this little handle, and you can read on this scale what the angle between the two faces is. Now, as you can imagine, this is not a method that you are likely to use in your research on your research crystals. So you're probably going to be growing much smaller crystals. This is a method that was used for minerals, for natural specimens, because most of those grew pretty big. And what could you do with that? Well, here are some quartz crystals. Quartz has very well-defined interfacial angles. For that matter, it often grows with several crystals together, and there's a certain angle between these crystals. So, people could measure these things and figure out, is this quartz or not? Because you may end up with a different mineral that looks fairly similar, right? It's kind of a fairly transparent crystal. But if you started measuring the angles on this one, you would certainly find that, no, this is not the same angle. For that matter, what is interesting here is if you look at some of these crystals, you can see some threefold symmetry here. Okay? That actually means that you either have something cubic or the squished or expanded cube. So just looking at those crystals, could very quickly say this is probably a cubic or rhombohedral crystal. So that's how you can measure some angles on real life specimens. Of course, nowadays, what would you do? You would take a piece of it, you would put it on a diffractometer, and you would have your answer very quickly. Okay? But that was the old methods. How you could actually find something out before people knew about diffraction. Here are some examples of crystal habits. Okay? That one's trivial, cube, we already talked about that. Now, a cubic crystal could also start growing in some kind of octahedral-like shapes. That is what would happen if your faces, your 6 cube faces, are actually the fastest growing faces of the crystal. You would form 6 corners instead of the faces. Okay? This is one of those things that often takes people by surprise, because when you see an octahedron, the first thing you would think is not cubic, right? But if it is actually a regular octahedron, then the crystal is most likely cubic. This one is actually a drawing of a real life crystal. This was a zircon. That material is tetragonal. Now, the first thing you would probably find here when you look at it is some kind of fourfold symmetry, right? Remember how we said in a tetragonal crystal A and B are equal, but C is different? So you could already say that the C axis is pointing in this direction, and it's growing faster under these conditions where this crystal formed than the A and B axes. Okay? So that is the things that you can figure out. This one would be another tetragonal crystal. Slightly different external shape, but still you see that fourfold symmetry. Of course, this is kind of a flat plane picture, but in real life that crystal would have fourfold symmetry. Okay? So, that's a brief overview of crystals. Any questions on crystals? Should be fairly straightforward. Okay. Now, as I said, we will be doing a little bit more with these. We are not living in the old days. We nowadays actually know something else. But we'll take a step back to how people first described crystals. What you saw on this last slide was numbers here, right? Somebody wrote numbers on these faces of the crystals. How do those numbers come about? Well, they're called Miller indices. And Miller indices, once again, were used before people knew about diffraction. As you will find out as this lecture proceeds, crystallographers use Miller indices a lot. We kind of live off them, okay? But the original definition still allows us to learn about Miller indices. So what we have here is two-dimensional crystals, okay? More difficult to draw in 3 dimensions, so you just do 2-dimensional crystals in X and Y. And I've drawn a bunch of unit cells here. Each of these little rectangles is a unit cell. And so in 3 dimensions you would describe crystal faces by Miller indices HKL. In 2 dimensions we would just be using H and K, right? Because we don't know about L. So what is a Miller index? Well, it's actually related to the unit cells, and it is defined as the reciprocal of the intersection of the plane with the unit cell axes. Now that sounds rather convoluted and difficult, so we'll be doing some exercises to actually figure out how that works, okay? One thing to keep in mind is all parallel planes, at least in the old days, when we are talking about crystal face indexing, can be described with the same indices, and you simply use the lowest numbers. So, here's our crystal lattice. Couple of rules. Number 1, I didn't define an origin there, did I? So can you choose your origin wherever you want to? If I don't define it, you can, right? It's up to you where you choose your origin. So whenever we try to index a crystal face, we'll pick what we call a convenient origin. Okay? As a rule of thumb, your origin cannot be on the face that you're trying to describe. Okay? But it should be adjacent to the face. So you don't want to be all the way, like if I'm describing this face down here, I don't want to pick my origin up here. That would not be helpful. I want to be at a unit cell corner adjacent to the crystal face I'm trying to describe. So, guess what all of you get to do now? Practice face indexing. We'll be taking turns. Who has a lot of courage here? Christy has courage. Pick a face, any face of your choosing. This drawing? This face. So there's Christy's face. How would we index that one? So we need the reciprocal of the intersection of this face or plane with the unit cell axis, right? And as we said, we can pick our origin wherever we want to. We cannot pick an origin on this line. So where should we pick an origin? 1 unit over. So any of these spots here would be good origins, right? So let's pick one. Let's just for the fun of it say our origin is right there. In the x direction, where do we intersect our unit cell axes? This is 0, plus 1, plus 2, plus 3, plus 4, minus 1. So we intersect the x-axis at minus 1. What's the reciprocal of minus 1? 1 divided by minus 1 is minus 1, right? So, minus 1, and crystallographers often write minus 1 like that. We call it 1 bar. We put the line above the 1. What that means is minus 1. Okay? Very good. You found your first index, Christy. Now, that is our origin. That's our plane. Where does it intersect the y-axis? It doesn't, right? So, what kind of an index do we assign? It never intersects it. So we call that infinity. What is 1 divided by infinity? 0. So the index of that face would be 1 bar, 0. Okay? Does that make sense? You picked a tough one to start with because it has a 0 index. But we figured it out. Good job. So, given that we started at the back of the room, let's continue. So, Indira, which face would you like to do? That one? All right. Where do you choose your origin? There? That would be a very good origin. It's adjacent to our face, but it's not on the face. Where does it intersect the x-axis? This is your origin. This is your x direction. Where does it intersect the x-axis? It does not? This one? This is the x-axis. Does that intersect this one? Yes. Where does it intersect it? If this is 0, minus 1. So once again, we have a 1 bar index. Now, where does it intersect the y-axis? plus 1. Very good. So the index of that face is 1 bar 1. Shoot, which face? Are you going to take the next one? That way we don't get lost. That one? All right. Where do you choose your origin? Any of these spots would be good, right? So, we choose that spot. Where do we intersect the x-axis? Plus 1. Where do we intersect the y-axis? Also plus 1. So that one is our 1, 1 face. Does that make sense to everybody? Stephen, there's your face. Here's our origin. Where do we intersect x? Plus 1. And y we never intersect, so it's 0. 1, 0. Chris. This one. There's your origin. X would be plus 1. Y would be minus 1. So that's the 1 bar face. Nick, you're next. Last face on this one. We'll pick any of these points, right? Adjacent but not on the line. Where do we intersect the x-axis? Do we? From here, plus 5 would be there. Does this face intersect that point? The crystal might intersect it, but does this face intersect that point? No. Does this face intersect this axis? Will it ever? It's parallel, right? So it won't. So what do we call that index? We claim it might intersect at infinity because we never know what happens at infinity, right? And 1 over infinity is 0, right? And how about the y-axis? Does it intersect the y-axis? At -1. All right. So we did the first one. Anil, which face do we start on the second one? That one? So we choose our origin here. What are our indices? Where do we intersect the x-axis? Plus 1? So we go from here to this. It doesn't intersect, so if we go this way on the x-axis, we never hit this face? -1. You just had your x-axis flipped. Yeah. So it's -1, 1 bar. When do we intersect the y-axis though? This is the y-axis. This is the face. It's not going to intersect. So what do we call the index? 0. Adam, it's your face.
Origin, 2 down and 1 over.
That one?
Yeah.
Here's our origin. Very good choice. Where do we intersect the x-axis?
-1.
-1. Where do we intersect y? So what are our indices?
1 bar and 1/2.
1 bar, 1/2. And that, as numbers, works. But the one thing that I didn't put down here is Miller indices are always supposed to be integers. So would it be 2 bar and 1? We can easily check that. Let's pick this origin. Where do we intersect x? -1/2, right? What's the reciprocal of -1/2? 2 bar. Where do we intersect y? 1. So yes, it is 2 bar 1. And as Adam nicely figured it out, if you come up with 1 bar 1/2, you can simply multiply the whole thing by 2 and you're there. Nathan, here's your face.
1 down.
1 down.
It'll never intersect the x-axis.
Correct. So our index is 0. Where will it intersect the y-axis? 0, 1. Anthony. And of course these lines really should go to the edge, so I apologize for that. Which one? That one? All right. Where do we intersect x? +1. Where do we intersect y? Is it 1? At 2. So what would be our indices? Reciprocal of 2? Would be 1, 1/2, but we said we want integers, right? So let's try it with this point here. Where would we intersect the x-axis? This is our point. How far along the x-axis to go here? 1/2. Reciprocal of 1/2? 2. Where would we be intersecting the y-axis? At 1. So that would be our 2, 1 face. All right. We aren't quite around the crystal yet. So Christy, you get another one. Zero and 1 bar. This is the x direction. So this face never intersects the x-axis. I think you got your axes switched. This face.
I'm doing that when I'm over 1, so you go.
So this is the x-axis, 1.
And it'll never intersect that. So 1 and 0.
Yeah, 1 and 0. There you go. Indira, here's yours. So let's take our origin there. The x-axis is going in this direction. 0, 1 bar. And those of you who thought that you're escaping the second round, too bad. Wrong thinking. True. There's your line. The new one that just came in. Just for you. Alright, so let's think about it, okay? We need something that is as close to the line as possible, but not on the line. Right? That's what we want. So, that point might work right there. So if you use that point, then we have to figure out, where do we intersect the x-axis? Minus 1/3, okay? Well, is it minus 1/3? It's difficult to see here, right? And you don't have a ruler, you can't walk up and measure it. So, what's the trick to figuring out? Is it minus 1/3 or something else? What I like to do is I go here and I say, how many times until I hit a corner again? That's actually 4 times. Okay? So it's actually 1/4. But I agree with you, just looking at it, 1/3 wouldn't have been a bad guess. But as you know that you need to go 4 times before you hit a corner, it's 1/4. So it's minus 1/4. What is the index? Four bar. Very good. And where do we intersect? Minus 1. So it would be 4 bar, 1 bar. Good. Oh, Stephen, I found a line for you. There's your line. Eight and 8-1. Everybody see that? This is the origin that he picked. And that one you certainly can't tell anymore without counting. But he counted, it takes 8 until we are there again, so it has to be 1/8. And plus 1 over here. Oh, Chris, that's yours. And we are starting the counting game. Good. So, origin should probably be one of these points, right? Which one do you want? The top or the bottom?
Top.
The top. There's your top.
Right.
So we need to figure out that one.
So I would count to the
How far across is that?
3.
1/3.
1/3.
So the index is
3.
3. And how far down do we have to go? 1/2 down, right? So minus 1/2, and the reciprocal of that is 2 bar. So that line is the 3-2 bar. If we cut our crystal that way, it was 3-2 bar. Yes? If you pick that one, what do you get? 3 bar and 2. Absolutely. What's the difference? Well, for face indexing, look at this one. Could we multiply the whole thing by minus 1 for face indexing? Yeah, right? It's a difference of perspective. From which side do you look at the crystal? That's what it boils down to, okay? As we will see once we go into crystallography, it matters what these signs are and what the multiples are. But for the purpose of faces, whether you call it face 3-2 bar or 3 bar 2, it's the same face. Your turn.
X is equal to 3. And Y is, or, 2 bar.
2 bar? Why 2 bar?
It is
That would require that it cuts at -1/2, right? Where does it cut? Where does it cut?
well, I was using the origin above that.
You're using the origin above that. In that case, it's not 1/3, right?
Oh, okay.
In that case, it would be 2/3,
Why?
because you're 2/3 across, right?
So then,
So the reciprocal of 2/3 would give us 3/2. So once again, we would have to relocate our origin.
so we want to go to one below.
So if you use that one, you get your 1/3, which is 3. What's that one? 1 bar. Very good. Yes?
You say the origin cannot be on the face. Does that also mean any face?
The problem is if your origin is on the face, where does the face cut your axis?
No, I mean like, could it be on any other face?
Yeah, because that's not the face we are looking at, right?
Like the one above the line there. Saying that.
Like this one?
No. That, yeah.
That? Yeah,
Okay.
that would be fine. But
It's just hard to see.
what we then would once again get is that we actually don't have integers, okay? And if there was something that was adjacent, yeah, that would be perfectly all right. The problem with being on the face is, where do we cut the axis? At 0, right? 1 divided by 0 is what? Infinity. We don't want indices of infinity because they mean nothing. So that's why we always go adjacent to the face. And in order to have integers, pick the one closest. All right, so we did that one. This is actually a good example where we can pick our origin on a face, okay? Want to pick that one for Nathan? It's not the face we are trying to index. So yeah, that's a good origin. So what are the indices? And what's the other one? What's the other one? So where did you choose your origin? There? That one? Right here? That one? Where? There? That's not an origin. That's your plane that you're indexing, right? So you need to take either that point or that point. That point? So where does your plane, this plane, cut your x-axis? From here to there, how far is that distance? How much of the unit cell? 1/4, right? So the index is 4. And where do we cut the y-axis? plus 1. So our index is 4, 1. There we go. Yes?
Another down.
Okay.
Can that be 1/3 the distance from the origin?
It would be difficult unless you measured, okay? But the way to look at it is 1, 2, 3, 4 before you're back. So assuming that the thing doesn't bend and wiggle on the way, it should be 1/4, right? So the safe way of doing it is just counting when do you hit a corner again. That's what I usually do. Unless I have a ruler, in which case I might just measure and then should come out as a 1/4 then.
So sir, is there any distance where you can
Not if we have a face. A face should be a nice smooth surface, right? 2 bar 1. It's getting fast here. These make sense to you? Good. Oh, come on. What happened? I did have 2 more. I have no clue where they went. I guess you two run lucky. You dodged a bullet. I hope this gave everybody a little bit of a feeling of how this works, okay? And you can go back to these and you can figure out, can I still do that? You can get together with people, okay? And you just take a pencil, you draw a line there. Make sure it does go through 2 corners of unit cells, okay? In that case, you can put an index to it. It might be some pretty big numbers, okay? But you can put an index to it. You can take a piece of the paper that has like the little squares on it, right? The math type paper. You can play these games with each other. Just draw any line there that goes through 2 corners of those squares. Challenge the other person. What are the indices of this one? Okay? That's how you can practice it. Now, if this gets to a point where you say, oh, this is easy, I know how to do it, good. If you're not at that point yet, practice. Okay? You will need to be able to do these things. Now, this is a 2-dimensional exercise. It works the same way in 3D. Okay? This is an example slide that shows you that. Here's a 2, 1, 3 phase. Now notice the important thing is your unit cell directions need to be defined for you to assign these things, okay? Your origin is back here. You have X, Y, and Z, or A, B, and C. You intersect the X-axis at 1/2 of this unit cell, okay? You intersect the Y-axis at the corner, at 1. You intersect the Z-axis at 1/3. Once again, you would need to measure that. That means it is a 2, 1, 3 phase. 1 divided by 1/2, 1 divided by 1, 1 divided by 1/3. Now, for phase indexing, all planes that are parallel can be described by the same indices. Okay? Because the indices really only give the direction. We just choose a different point of origin, we get the same indices back. So, all of these parallel planes could be described by the same set of indices. That also means that sometimes all you have to do is find what is the most convenient parallel plane for you. So you can move that line 1 over as long as you keep it parallel. It's the same as moving your origin, okay? This one shows you what was on that prior slide when I said they put numbers on there. The 100 phase, the 010 phase, the 001 phase. And that is how crystallographers work, okay? They put numbers to phases, and as we will see later, we will be putting numbers to what we call crystal lattice planes, okay? So it's very important that you get some feeling for how these Miller indices work. We will be talking about them again. We have practiced a little bit. I hope everybody has picked up on it to some extent, okay? All right, now we do have a little field trip again today, because life is pretty boring without field trips. So we'll actually go upstairs. If you think that these crystals were pretty cool, if you could return them to this tray, that would be good. They actually have a crystal museum upstairs, and they have some very nice specimens in there. So we'll just go there, and you can look around, and then you can disappear and do whatever else.